In this video, as part of reinforcement learning, we will study general reinforcement learning and Q learning. So in general, we have something called agent and the environment, and the agent may be some device, maybe a robot, which has to carry out which has to go to certain states, and it has to carry out certain actions. But when we actually talk in terms of some mathematics, the agent may be an algorithm. So we have something called agent and something called environment. The environment may be certain conditions and constraints. Basically, you can understand that the algorithm has certain functions. The functions have to move to certain states, certain actions have to be taken, and certain states, the algorithm has to take certain functions to certain states. We define one quite general formulation of the problem based on Markov decision process. In a Markov decision process, the agent can perceive a set capital S of distinct states and has a set capital A of actions that it can perform. At each discrete time state t, the agent senses the current state st, chooses a current action at, and performs it. Here you can understand the agent means some kind of algorithm. The algorithm responds by generating a reward rt is equal to r as a function of st and at, and by producing the succeeding state st plus 1 is equal to delta function of st comma at. See, as of now we are talking in general, and this may not be actually exactly implemented, and we'll see step by step understand this, and we'll go to some function called Q function. Just let us understand some logic. Here the functions delta and r are dependent on current states only and not dependent on past states and actions. That is what is called Markov decision processes. In Markov decision processes, the future actions and states are going to be dependent on only the current states, and they are not going to be dependent on the past states and past actions. In an MDP, the functions delta as a function of st comma at and r as a function of st comma at depend only on the current state and action and not on the earlier states or actions, as I told. Now, there may be so many states and so many actions. In theory, it may be uncountable, but we are going to talk only some finite number of states and finite number of actions. Now, these functions, the functions which are talked in algorithms, and in this case delta and r, they may be deterministic or non-deterministic. When we say deterministic, without using some probability functions, and when we say non-deterministic, we may have to use the probability theory. As of now, firstly we will see these deterministic cases, then we will move on to non-deterministic cases. The task of the agent or algorithm is to learn a policy pi. Now, what is that policy? S is mapped to A, or from S we are taking some actions. S is mapped to some capital A, where capital A stands for states and capital A stands for actions. So that is selecting next action AT based on the current observed state ST. That is the policy pi of ST is equal to AT. The algorithm has to learn the best policy. So one obvious approach is to learn the policy that produces the greatest possible cumulative reward over time. Now, to state this requirement more precisely, we define the cumulative value. V pi of st achieved by following an arbitrary policy pi from an arbitrary initial state, as the next slide shows. V pi of st, right, we are going to form some cumulative reward. V pi of st is equal to RT, that is immediate reward, plus gamma into RT plus 1, which is the next reward, plus gamma squared into RT plus 2, and plus and so on, which can be written in a compact form as sigma I is equal to 0 to infinity gamma to the power I or T plus I. So this is, we call it as cumulative reward function. Now here gamma, which is greater than or equal to 0 or less than 1, is a constant that determines the relative value of delayed versus immediate rewards. See, this we call it as immediate reward. These all things we call it as some delayed rewards. In particular, rewards received I time steps into the future are discounted exponentially by a factor of gamma to the power I. Now note that if we set gamma is equal to 0, only the immediate reward is considered. You can see in the expression. As we set gamma closer to 1, the future rewards are given a greater emphasis or more considerations. That from this you can understand, if gamma increases, these factors are going to increase, more considerations are going to be given. Now other definitions of total reward have also been explored in theory. For example, finite horizon award, which is nothing but without multiplying by gamma, just adding all the rewards, sum of or T plus I, where I is something 0 to some h. This considers the undiscounted sum of rewards. There is no discounting here, multiplying by gamma. See, gamma is less than 1, that is why we call it as a discounting. Considers the undiscounted sum of rewards over a finite number h of steps. Now another possibility is just a sum and divide by the number of states. Another possibility is average reward, limit h tends to infinity, 1 by h sigma I to h or t plus I, which can be called as something like long-term average, because h tends to infinity. Now we require that the algorithm learns a policy pi that maximizes V pi of s for all states s. Now we will call such a policy as an optimal policy and denoted it by pi star. Now what is a pi star? Pi star is equal to arg max for all pi, V pi of s for all s. That V pi of s for all s. And this maximum we have to find with respect to this pi. For each pi we have to calculate this V pi function, right? And which pi gives the highest one, that is a policy we will go for. That is what is the meaning of star here. And we can write V pi star as the evaluation function, but shortly we will write it as V star of s. Gives the maximum discounted cumulative reward that can be obtained starting from state s. Now, implementing the previous expression is very difficult because we don't have delta function, right, and reward function. All those functions we don't have. So now, what evaluation function should the algorithm attempt to learn? One obvious choice is V star. The algorithm should prefer state 1 over state 2 whenever V star of S1 is greater than V star of S2, right? Because the cumulative future reward will be greater for S2. Now, we talk in terms of states, but actually we should talk in terms of actions. So we are going to talk, the next functions are this Q algorithm in terms of actions. The optimal action in state S, the action A, we are not telling state, we are telling action A, that maximizes the sum of the immediate reward or S comma A plus the value of V star of the immediate successor state discounted by gamma. That is what we write here. The policy, the best policy is arg max, which is in terms of with respect to actions, not states, of R S comma A plus gamma into V star delta of S comma A. Now the problem comes in, knowing this delta function, R function, all these things, right? That is the reason we will better go for a new kind of algorithm, something called this Q algorithm. In cases where either delta or R is unknown, learning V star is unfortunately of no use for selecting optimal actions because the algorithm cannot evaluate the above equation. Now, what evaluation function should the agent use in this more general setting? The evaluation function is the Q function. Let us rewrite in terms of Q, and then we will understand that some kind of iterative process will take place where we need not know delta or all these functions. Now, define Q S comma A, which is the current state and current action, is equal to R S comma A plus gamma into V star delta S comma A. Right? So we can write based on the previous expression, this expression. Now we are defining this is nothing but a Q. We are defining this as Q. So we can write it as pi star is equal to arg max with respect to actions Q S comma A. Now what's new here is that it shows that if the algorithm learns a Q function instead of this V star function, it will be able to select optimal actions even when it has no knowledge about the functions R comma delta. So basically we are going to follow some iterative process. Let us see next to the algorithm. So the Q learning algorithm, for each S comma A, initialize the table entry or the matrix Q to 0. We are going to initialize the matrix to 0. See, all these terms these are all states, these are all actions. We have initialized to 0. Observe the current state. Now do for ever. Select an action randomly and execute it. Select an action randomly and execute it. Receive immediate reward or observe the new state S dash. Now update the matrix or table entry for Q S comma A as follows. R plus gamma max with respect to A, Q S dash comma A dash. That is A dash. Now A dash is all actions. S dash is next state. Now this value is going to be assigned to the previous one, that Q S comma A. Here S is some current state. This is my next state. Next, what I am going to do, this next state is going to be converted as the present state. That is S dash is going to be assigned to S. We can also write like this: Q state comma action is equal to R. R is reward function, state comma action plus gamma. We have written in terms of words, gamma into maximum in terms of actions. Q, now we have written next state as I told you before. Next state, S dash, comma all actions. That is very important, all actions, because we are writing max with respect to all actions. Right. So let us consider an example and finish this video. There is a house which has many rooms, and we have to go to, our goal is to reach something called fifth point or fifth room. We may be anywhere, and we have to write an algorithm which is the shortest path to go from some particular state to number 5. Goal 5 is my goal state. So let us write this. There are paths shown here, and with respect to all these things, we have drawn some state and action diagram. This is, you can understand, this is self-explanatory only. Now from 1, there is a direct path to 5. So from 5 to 1 also there is a direct path that you can find here, right? And 5 to 5 also I can go. Now 2 to 3 and 3 to 2 connection is there. 2 to 3, 3 to 2 connection is there. So like this diagram is drawn. Now we initialize this matrix, all the elements to 0. These are all, as I told you before, these are all states and these are all actions. Now reward function, we award reward only to, which is leading to the goal point. So number 1 is leading to